All right. Chapter 2. One-dimensional kinematics. Throughout this course, we're going to use a few words to describe the way in which things move. The key quantities are going to be those of position, which we might use an x or a y, or a combination of both, or a combination of both to describe. So that's a position. Displacement, I'll stick with the x for here. So that's a change in position. And we're going to put a hat on that, which indicates that it is a vector quantity. For a lot of these vector quantities, which means they care about a size, an amount, and a direction, you can also have a scalar quantity. That would be distance. And so scalar quantities only have an amount, while vector quantities have an amount or a magnitude and a direction. That direction part's going to come into play again in chapter 3 and a little bit in this chapter. We'll have in one dimension, you can go plus or minus, meaning forward or backward. Velocity, which is a displacement divided by a passage of time. And since displacement is a vector quantity, so is velocity. You can also have, so that's velocity, which is again a vector. There is a scalar part to velocity, which is speed. Measure of how fast you're going. Speed does not care about direction, velocity does. And then finally, you can have an acceleration, which has the same type of relation to velocity as velocity does to displacement. That is, acceleration is defined as a change in velocity divided by a change in time, which is also a vector quantity. You'll notice that hidden, tucked away in these things, is an implicit understanding of time. And that one's trickier to define, but experimentally, we kind of know it when we see it, and we've come up with good ways of measuring it. So intuitively, we'll have the sense that time is passing. We know how to use watches, even fancier equipment than watches. So this is kind of the general rundown of what we're talking about. All right, let's talk about motion in one dimension. That is motion along a line. When you're constrained to move along a line, you can either move one direction or the other. And so by convention, we'll tend to assign one direction positive, we'll make that the right direction, and one direction negative. To track this, it's useful to create a coordinate system. So we'll call this the x-axis, and we'll create an origin. An origin is an arbitrary reference point that you're going to say is position 0. And then you can keep track of distances in certain directions relative to the origin. So 1, 2, 3, 4, 5. That would be plus 5. And 1, 2, 3, 4, 5. That would be minus 5. Right? And so you could be at different locations. You could be at position +5, you could be at position 0, you could be at position -5. Well, that's just where you are, but you can change your position. So let's say we started at position 5. We'll call that an initial position. So that's X initial. And you ended at position -5. Well, then you'd have a displacement, a change in your position. And anytime we have this delta, it just means change. And all that means is do a subtraction. Take the final of the thing, in this case a position, and subtract from it the initial of the thing. Well, as we said, these are vector quantities in that they care about direction. And in this case, our final position would be -5 units. We didn't define units, but often you would put what your unit is on your coordinate axis, minus +5 units. And we would see that our displacement would be -10 units. And we can check this. Where did we start? Here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Indeed, we went 10 units to the left. So that's displacement in one dimension. One thing about displacement is it doesn't care about how you get there. So for example, we could have the same displacement if we would have gone, let's choose a different color. Let's say we started at 5, and then we went to 1, and then we went to, I don't know, 7, 8, and then we went to 5. Well, if we only cared about still this being the initial point in time and this being the final point in time, then the calculation would still be the same, even though the path was different, meaning you could have different distances of travel when you accomplish the exact same displacement. All right. Let's talk velocities. So first we'll talk about things that move with a constant velocity. If something has a constant velocity, well, we know that the definition of velocity is a change in position over a change in time. I'm going to use the subscript x to say that our constant velocity is along the x direction. Well, in this case, I can see that graphically, what velocity is the slope of a position versus time graph, right? Where that would be delta x, that would be delta t, right? And so if I were to simply rearrange this, what I could see is that delta x will just be equal to v sub x delta t if I have a constant velocity. I could write this a different way and say that my final position during some period of time when I have a constant velocity, it's just equal to my initial position plus whatever my constant velocity is times the passage of time. In this case, my velocity would be positive. I can also have negative velocity, meaning the slope could be downward, in which case my position would go towards smaller or more negative numbers with time. Either way, I should have a fixed slope if I have a constant velocity. Let's see if we can go the other way. If I were to have plotted instead velocity versus time, let's say we had 0, 1, 2. And these were in, let's say, units of distance per time, let's say per second. So I have 1 unit per second of velocity, it's positive. Well, I know from that velocity is equal to delta x over delta t. So then let's say I knew what delta t was. Let's say that's 0 seconds, and that's 10 seconds. All right, well, in this period of time, I can see that 1 unit per second times 10 seconds would give me 10 units of displacement. This would be my displacement in this period of time. And notice something. 1 times 10 happens to be the bounded area beneath the line. It's not really a curve here, but it will end up being between the curve and a time of 0, right? So the value of velocity equal to 0, velocity of 0. So between 0 velocity and the velocity I have from the initial point in time to the final point in time, in this case, makes a rectangle. The area of that rectangle will be my displacement, meaning graphically, I can get displacement from a graph of velocity versus time by taking the area between the graphed line or curve and the value of velocity equal to 0. Okay, let's try now constant acceleration. If you have a constant acceleration, well, then it must have a similar relationship with velocity versus time that velocity had with a position versus time. That is, if I have a constant acceleration, then my velocity must change at a fixed rate. Let's say something like that. And since the definition of acceleration is a change in velocity over a change in time, then the slope of a graph of velocity versus time, this will have a slope, must be that constant acceleration. All right, go up, that's a change in velocity. Go over, that's a change in time. Slope is rise over run, which means that the slope is equal to delta V over delta T, which is the definition of acceleration. So at any given time, you can get the velocity, the acceleration at a given instance in time if you can find the slope of a velocity versus time graph at that point in time. How does that work if you have a curve? Let's say velocity versus time wasn't a line, but it instead looked like this. Well, what you do there is you can kind of do two things. You can take the tangent to the curve such that at this point, your slope looks like that. At this point, your slope looks like this. That's the tangent to the curve. That's like trying to lay a ruler against the curve so the ruler only touches the curve at one place. Or you could kind of take the approach that what would happen if I zoomed in on this and kept zooming and kept zooming? Well, if I zoomed in on this enough, eventually what I would see is something that looks like that. And if I zoomed in again, I'd see something that looks flat eventually. And I can say, okay, the slope of that thing is the slope at the point. So the slope at this point is effectively 0. And the slope at this point, if I zoomed in, it would look like that. So that would be some positive slope that's steep. Right? So you can get slopes from curves at a point. That slope at that point is the acceleration if what you're graphing is velocity versus time. Okay. What happens then if we were to be graphing? All right, let's go back to our graph that had constant acceleration, that had velocity versus time, like this, where the slope is the acceleration. How would I determine what the position versus time graph should look like? Well, I know that the area between the velocity versus time graph and a velocity of 0 for a given time period is going to be equal to my displacement in that time. So let's make a different graph. Let's make it so it doesn't start at 0, just to be more general. So let's say instead we had something that had an initial velocity that was not 0, had a constant acceleration. In that case, if I wanted to know what's the displacement between time 0 and time final, i.e. delta t, well, I would take the area. So delta x is equal to the area beneath that curve. Well, the area beneath that curve is comprised of two shapes, a rectangle and a triangle. The area of the rectangle is just my initial velocity, using a naught here for initial, multiplied by how much time passed. That's the area of the rectangle. The area of the triangle is, well, it's a right triangle, and I know that for a right triangle, it's 1/2 the base, which is delta t, times the height, which in this case is delta v. V final minus V initial. All right. So this is delta V. But I also know the definition of acceleration is delta V over delta T, meaning delta V is equal to A times delta T. So I could put that there. And what I'll get is a new equation that says delta X is equal to my initial velocity times however much time period time goes by while I'm traveling with a constant acceleration, plus 1/2 whatever my constant acceleration is in that direction, multiplied by the change in time squared. And that's a new equation that we can derive from a graphical analysis. Right, so now we've got a few equations. We've got for constant velocity that delta x equals v delta t. For constant acceleration, we know that delta v equals a delta t. And we now also know that delta x can be expressed as v initial delta t plus 1/2 a constant delta t squared. If I put these two equations together, I can actually derive a third equation that does not depend on time. What that equation will say is that my final velocity in a given direction squared is equal to my initial velocity in that direction squared plus twice my constant acceleration in whatever direction that is, times the displacement I undergo in that direction, all within the same time period. So I've got 1, 2, 3 kinematic equations. All right. 1D kinematics, graphical analysis example. Let's make a random velocity versus time graph. And we can start at any old place we want. Start it at the origin. Go. And let's see, how do we want this thing to go? We can make it go up. That, then go down, go like that. Random graph, right? We choose velocity versus time because it gives us the fullest range of approaches, meaning you can get a position versus time graph from this, and you can also get an acceleration versus time graph from this. And one will care about the position and one will care about the slope. So how would we get a position versus time graph from this? Well, in that case, we know that at every point in time, the position of this graph tells us the slope of this graph. Nothing tells us the position of the position versus time graph, meaning we don't know where it starts. That's arbitrary. But what we know is wherever we pick for it to start, from that point forward, the position of the graph up here tells us what the slope of the graph down here must be. Initially, the position is 0, so the slope must initially be close to flat, meaning slope of 0. And slowly, the position here gets more and more positive until about there. That means that the slope must be getting increasingly more and more positive until we reach this time. There's going to be some artistic license in this drawing, but we might get something that looks kind of like that. All right. Once we hit this point in time, there's a little time period where the slope stays roughly constant. After that, the position stays positive, but decreases to 0 by about this time. That means we will keep going uphill, but the hill will get less steep until about there, in which case the slope will again be 0. After that point in time, the slope gets negative, and increasingly more so until about this point in time. Well, that means between these 2 points in time, we would get an increasingly negative slope. Something like that. And then from this point to about this point, we have a constant negative value, which means we'd have a constant negative slope. And then from this point to the final point, the slope stays negative, but it becomes a smaller value, which means we continue to go downhill, but we do so at a slower and slower rate. Something like that. And so in that way, we've just reconstructed a position versus time graph from a velocity versus time graph. What if, instead, we wanted to see what the acceleration versus time should be looking like? Well, now we would take the slope and we would turn it into the position. Initially, the slope is positive, and it's actually kind of the steepest positive it will ever be. So we will start off at whatever our greatest acceleration will be. That slope slowly gets smaller until it becomes about flat at this point here. So what would happen then is our position would slowly become smaller and smaller until it reached about 0 there. All right. All right. The slope then stays 0 for a little bit till about that point, at which point it abruptly becomes sharply negative and nearly constant for a short period of time. That means that we would abruptly become a negative value. And then slowly, that negative value would then get a little smaller. So we get an abrupt shift towards negative, and then here it gets less negative until about over here it's back to 0. So you'd have something like that. It then stays 0 between these 2 points. That's roughly 0. And then becomes slightly positive and increasingly so, which would look something like that. So this acceleration versus time graph would be compatible with this velocity versus time graph, which in turn would be compatible with that position versus time graph.